Yeah, let's start.
Okay, so, right, the recording is on, right? Great. So, hi everyone. So, welcome to the fourth talk of the Wednesday nights on Petronets and their extensions. So, for the European listeners, these are actually not nights today, it's the morning, but for someone from far away from Europe, it's actually the evening, so we are staying consistent to, at least with the nights for our presenters. And today, our talk concerns the applications of the Petrinet theory. So specifically, we will be looking into the very hot topic of conformance checking that actually has gained momentum in the last years. And there is a challenge that many researchers face while working on this topic, on the techniques used in conformance checking. That is the definition of suitable, appropriate measures that help to assess the level of correspondence between the log and the model. So today, Artyom will talk about his recent work on conformance measures for process mining based on the concept of entropy, right, which comes from the information theory. So, Artyom, the virtual floor is yours.
Thank you, Andy. Thank you for this introduction. Yes, my name is Artem Poliviany. I am senior lecturer at the School of Computing and Information Systems here at the University of Melbourne. And it's my pleasure to present to you today our work on conformance checking. Andy did a good job introducing the importance of the topic, so I will just proceed with the slides. So this picture already appeared in this series of workshops. I saw Dirk Valent was using a sketch of this picture. It's taken from the book of Will van der Waals on process mining, and it basically summarizes the main problems, well, the setup, of course, but also the main problems that process mining field addresses. So we all live in the real world, right? I hope at least you agree with that. And we want to improve the way we live in this real world. And one way to do that, we invented software systems, those automated systems that help us, support us in this real world, but also help us to control it, the world around us. So this is a link between the world and software systems. But then those systems, they of course generate a lot of used information that we can later analyze and make certain inferences and try to improve the status quo. And those recordings are stored in event logs. So those are observations of how processes, mainly business processes, but can be other types of processes, evolve in the real world. And then process mining, right, addresses three main problems. These are the three core problems. Given the data, we want to discover the process. So what happens in the real world? So we want to discover a model of what was observed, to understand what was happening, to understand how we can improve what will happen in the future. We want to check conformance of models. If we have models either designed or discovered automatically, we want to check how well those models represent the data, how well they represent event logs. And maybe we want to enhance our models if they already exist. So we want to study what can we learn from event logs, what were good practices, and then enhance our models so that future processes are executed better. So this is what we do in process mining, and the topic, of course, today will be conformance. So we want to check how good do our models represent the data. And this can be either models learned automatically from event logs using discovery techniques, or alternative, this can be existing models designed by an analyst by hand, and then, well, we just want to check how well they match the reality. Okay, so this is process mining in the nutshell. But if we do that, if we apply process discovery techniques blindly, well, we discover what we know as spaghetti processes. So of course, reality is inherently complex, And if you just apply discovery techniques without any sophisticated filtering techniques, you will get something that you see on this slide. So on the left, you see a model from the book of Will van der Waals. On the right-hand side, there is one model generated by my PhD student, Zihan Su, right? So it's really a nice piece of art that you see on this slide, but is it useful to analysts? Probably not. So how can we get more useful? So then what we do, we of course filter and simplify these models. Let's call them lasagna models, just to refer to them as more structured models. These are some examples of models that industry vendors discover from event logs and then propose to their customers as a product to analyze what is happening in their businesses, etc. So we are trying to get from this mess, from this disorder, to something that is structured but still represents the reality. And of course, you can imagine that there are many ways to carve these lasagna processes from those spaghetti processes. And well, which way is a better one is hard to envision and understand. And well, there can be many methods proposed how to do that. So, so what is conformance checking doing? So conformance checking is trying to compare traces that are described by a process model here on the right-hand side. Well, this is a Petri net, right? Matches the topic of this series. And on the left-hand side, you see a simple event log with 5 different distinct types of traces occurring at different frequencies. And then we want to understand how well that model on the right-hand side describes the data on the left-hand side. And this can be a spaghetti model, it can be a lasagna model, it can be any model on the right-hand side. So it's just that for simplicity, I have a simple, small model, which is shown on this slide. So there are different notions that we can use. So the most standard ones, the simple ones, are precision and fitness, or also, as I call it, recall. So what do those measures try to assess? So precision checks if a process model describes some behavior which is not in the log, so, and penalizes it. So this is not desired behavior if a model describes traces outside of the log. So we want to minimize those traces. And this model on the right-hand side, it describes just one trace which is not in the log. So it's kind of, we can say that this is a model with good precision. Recall, on the other hand, wants a model to describe all the traces from the log. And so we want to cover all the traces from the log so that they are, we can replay them by the model. And also here you can see, if you replay these traces on the process model, that here the fitness is quite good. Okay, so let's move on. And let's talk about what was done in classical conformance checking. What was done for the past 20 years, how this problem is addressed by academics worldwide, also primarily in Eindhoven. But also, before I proceed, I want to thank all my collaborators who contributed to the content that I'll be presenting on the next slide. So we will be presenting also our techniques, how we cope with this problem. So let's go a bit deeper and we'll understand how conformance checking can work. So we have the same event log, and then we can be discovering candidate models, right? So here on the left, you see 2 models, a single trace model and a flower model. So a single trace model describes a single trace, A, B, D, E, I, from the log. It's a frequent trace, right? But it's not all the traces that we see in the log. So what we can say that the precision is very good, right? But fitness is a bit bad, right? Doing bad because we're just fitting one trace into the model. Others are not that frequent, but still, if you think of them in combination, altogether, we can say that we can do better on fitness. So bottom of this slide, well, it has perfect fitness. The flower model can replay all the traces of the alphabet, right, on the characters that are included in the model. So all the traces from the log can be replayed, but it has very bad precision because this model, of course, describes all the possible sequences of characters, and many of them are not included in the log. So that is an example of a model where precision is very good and fitness is very good and precision is very bad. And of course, we want to find models that are somewhere in between. Like, for example, these candidates on the right-hand side, process model 2 and process model 3. Well, we can conclude that these models have good fitness. They can replay all the traces from event log, but about precision, it's hard to tell, right? I mean, it describes extra traces. It doesn't describe all possible. They both don't describe all possible traces on the alphabet. But yeah, how good should precision be? How it's kind of a problem, right? So it's a real problem, and that's a problem that we'll try to resolve in this presentation. Proceeding, let me introduce precision and recall from other areas. So right, these are standard measures, not only in process mining. Precision and recall are used in information retrieval, they're used in classification, pattern recognition, etc. And let me talk about information retrieval, because I also in the past worked in information retrieval a bit when I was doing my master thesis a long time ago. And what do we do in information retrieval? So in information retrieval, we have a document collection, all web pages on the internet, and then we have a query, right? So the query, you go to Google, Bing, Yahoo, whatever is your favorite search engine on the web. So we type that query, we send the query to information retrieval engine, and that engine gives us a set of retrieved documents, this blue circle on this slide. But the query also determines the set of relevant documents. Right, so this is the green circle on the slide. And then if we just operate with these two sets, precision is defined as the quotient of the relevant retrieved documents to the retrieved documents, and recall is the quotients on the relevant retrieved documents to the relevant documents. So here, if I just consider these dots being the documents and I count them, I can just do simple counting. Well, I will establish that precision is equal to 3/4, right? And recall is equal to 3/5. Nothing special. We can do a simple arithmetic and compute those numbers. So let me now transfer this analogy to conformance checking in process mining. So instead of collection of documents, I now have a system of traces that is a system that I want to discover, so to say. And then I have an event log, which is like my query. So what I do, so this system is not known for us. This is some envisioned systems that generated event log, and we want to discover it. So we feed, well, event log and maybe knowledge, some knowledge about the system if it's available. Usually it's just an event log into that discovery algorithm. And as an outcome, we get a model, the discovered model, which is a collection of traces. Right? So it describes traces that I here denote with a capital M. But of course, log is for us relevant traces, a set of relevant traces. These are the traces we want to see in that model that we discover. And if we just continue, well, precision can be defined like that, the quotient of the number of common traces in the local model divided by the number of traces in the model, whereas recall is defined by the share of common traces, number of those common traces by the number of traces in the log. And if I go back to the examples I showed to you before, I use that event log 1 and process model 1 that I showed to you on previous slides. I can also count those quantities, and you'll see that precision is 5, 6, and recall is 5 over 5, so it's 1. There is only one trace difference between log and model. So model, in addition to log, describes a trace A, C, G, H, D, F, I. So that's what happens in this situation. So all solved, right? So we know how to do conformance checking, no problems whatsoever. Well, not exactly. So that would be perfect situation if not, at least not 2 issues, or at least 2 issues that are present in this story I just told you. So first problem, that we are dealing with infinite number of traces that the model can describe. So if I look at a process model 2, right, we can notice that it has loops. So here at the bottom we have steps G and H, and they can interleave. They can, first of all, they can occur multiple times, and those multiple occurrences can interleave, generating an infinite number of possible sequences of G and H that also interleave with the rest of the transitions here in the Petri net. And if we just do the counting of traces, well, we will have infinite number of traces in a model, and well, precision is either undefined, or we will need to adapt some convention and say, well, it's then 0 or something, or 1, or whatever you prefer. But that means we blur the analysis, right? For all those models that contain cycles, and probably many of them will contain cycles, because as we want to simplify models, we squeeze more and more behavior in them. We need to introduce cycles. So basically, such a technique for conformance checking will be pretty much useless. So this is the first problem. Second problem is to do with partially matching traces. So here I have process model 4 now captured as a automaton, right? Deterministic finite automaton, and I simply went log of 1 trace. So of course the model cannot replace this trace. It doesn't describe trace A, B, B, C, E, and therefore if I just do counting, though I can do counting in this case, right? It's model describes finite amount of traces. I can do counting both in the model and the log. Well, those precision and recall values will equal to 0. But intuitively, we kind of may feel that we want to express that similarity of traces in the log with the traces in the model, because there is a trace that starts, let's say, with A, B in the model, right? And then if we skip another B here in the log, we can proceed with C. Then if we skip D in the model, we can finish with E, which is also a matching step. So there is some degree of similarity between traces in the model and the log. So these are 2 problems that don't allow us to use that simple approach that I showed to you on the previous slides. So let's see what we will propose to solve these problems. So in order to cope with problem 1, which is infinite number of traces, we propose not to count them, but estimate them by the notion of topological entropy. So this is the definition of topological entropy. And instead of just measuring the cardinality of the language, we measure its topological entropy. So it's kind of a measure, in simple terms, a measure of complexity of the language, how fast the language branches as we look further in the future with the subsequent steps in the behavior in the traces. So if I look a bit closer into this formula, so B is an automaton, deterministic finite automaton, which describes the language, either the log, traces from the log, or the traces from the model. There is one technicality. In order to compute this measure, that should be an ergodic automaton, meaning that if I look at the states of that automaton, there should exist a path between any 2 pairs of states. So you can imagine that this is not always the case. So we have one technical step, which we then show doesn't harm our results, right? So through proofs, we show that we achieve what we want to achieve, and I'll talk about that also a bit later, what we achieve with this way of measuring conformance. So we just connect the terminal state with the initial state in the automaton it's a bit more involved if you have multiple terminating steps, but essentially that's what we are doing to obtain the ergodic automaton from either log behavior or from the model behavior. Oops, sorry, I just ran in front. So then what we do, so Cn of B is the set of all traces of that automaton of length n. So here we are counting the number of traces of length n described by automaton B. And then, of course, you also puzzle. So, but how to compute this, right? So this is some limit, n runs to infinity. So we need to construct a sequence of values, which is infinite. So how to just computationally obtain it? But the theory tells us that this entropy is equal to so-called Perron-Frobenius eigenvalue. So if I construct an adjacency matrix of my automaton and then compute their eigenvalues, so the largest eigenvalue is a Perron-Frobenius eigenvalue. I'm saying a largest because there can be several eigenvalues with the same of the same value, and any of them will do for us, right? So if we find such eigenvalue, we know the value of that entropy. So this is how we do computation of that entropy algorithmically. So we construct the adjacency matrix and we get the largest eigenvalue of that matrix. So then we define precision and recall as quotient at the bottom of this slide. Right, so instead of just doing cardinality of sets, we are doing the entropies, where this entropy with a black dot is nothing but an entropy of that short-circuited automaton, right, where we ensure that the automaton is ergodic to be able to then compute correct values of the entropy. All right. Sorry, my mouse behaves strangely, it jumps back and forth. Wait, oh, yeah, now this one. So let's take a look at some examples. So let's take a look at two simple models, M1 and M2, and three logs, L1, L2, L3. And this is, well, not that simple Venn diagram of the traces that logs and models describe, right? So these are the relationships of those languages of models and logs. So if I now just fire that theory and compute precision and recall as shown on the previous slide, I obtain a bunch of values, right? So you see here model and log in the first two columns, that's all the possible combinations. And then in the third and the fourth column, you see precision and recall values. And the question is now, well, okay, these are some values, but they look like magic numbers, right? So why this and not other numbers? So what can we see from these numbers? And you're absolutely right. Without any kind of reasoning, these are just magic numbers. And usually we want to say that 0 is a bad result. 0 is absolutely no similarity between model and log. And 1 is full similarity, perfect match between model and log. And if I look at first at these values of 0s and 1 here, so let's take a look at, let's say model 1 and log 1. So model 1 is this area, so A, B, B, A, and A, C trace. And log 1 is completely inside of the traces of model 1. So yeah, it's a perfect fitness. So model M1 describes all the traces from log 1. So fitness should be 1, and it is 1, so as expected. So on the other hand, if you look at model M1 and log 3, well, log 3 is over here. It has no common traces with model 1. So we expect that that value of precision and recall both will be 0. And here, of course, we see that this is indeed the case. Both precision and recall are zeros. Note that I'm now talking about the case of exact matching of traces. So, right, we are not yet looking how to resolve problem number 2 of partial matching of traces. So at least ones and zeros we can explain, right? So this is not surprising here what we see. They're all meaningful if you just take your time and examine this diagram and table closer. So, but what happens with other numbers, right? So how to understand other numbers? And to do that, we use properties for conformance checking measures. So this is the work of Nick Tax and his collaborators. And back in 2018, actually this was the first work on looking at properties of conformance measures. So what they did, they proposed 5 axioms, what they call axioms. I prefer to call them properties. It's not a big deal, but 5 axioms which should hold for precision measure, specifically for precision measure, because that problem of infinite number of traces in the model happens only with precision. For recall, we can always compute intersection of log and model, and that's always finite, and also the number of traces in the logs that we put in the denominator is also finite, so there's no problem of infinite traces with recall. It's a problem of precision. So these 5 axioms say that well, precision should be a deterministic measure. If I give same log and model as input, I should be getting the same precision score as a result, right? Very intuitive. Axiom 2 says that if I have a log and 2 models and their relationship on languages is like this, so L1 is included in M1 and M1 is included in M2, then precision of log 1 with respect to model 2 is less than or equal of precision of log 1 and M1. Well, that's kind of intuitive. M1 describes less extra traces compared to log 1, so it's closer to log 1, so its precision is better than that one of M2. So if I have a flower model, then this is absolutely absolutely worst precision that can happen, right? That flower model describes all possible traces, so axiom 3 says that flower model is absolutely worst with respect to precision. Axiom 4 well says that precisions of an event log on 2 language equivalent models should be equal. So precision is independent of this representation of my model. Right? I can draw my model like that, or another way, if they have equivalent languages, my precision with respect to a given log is the same value. And also axiom 5, which relates log to model. And then, well, clearly, precision between log 1 and M1 is worse than precision of log 2 and M1, well, because L2 covers more of the behavior of M1. So with respect to L2, yes, model M1 describes less extra traces. So this is what happens with these properties. And then they did a simple analysis. They looked at some state-of-the-art techniques in conformance checking, state-of-the-art precision measures, well, 6 of them. And then they found out that many of these techniques don't satisfy many of these properties. So these crosses are the examples, well, these are the indications that the corresponding technique doesn't satisfy the corresponding property. So either they did it by example or by proof, they demonstrated that this will not hold. And here is only one tick, meaning that that property holds, right? So that's actually discovering more non-holding properties than holding properties. Okay, so I thought that's interesting. Actually, this was at the time I started working on these measures of precision and recall. And then that we figure out that the entropy-based precision satisfies all those 5 axioms. Right, so I mean, you can find the details in the paper, but that's really so that this our measure of precision satisfies all these 5 properties, and even it satisfies stronger properties that we demonstrate. So these are, I say that these are properties A2 prime and A5 prime, because they are pretty much same as A2 and A5, with only single difference, that instead of less than equal constraint, we have less than constraint, so more stricter constraint. Actually, it's a small difference, but very important difference in my opinion. I just want to stress this here. Well, because it allows us to spot a difference, even if the difference is tiny, is in a single trace. So if, for example, here, log 1 differs with model 1 in 1 trace, and model 1 differs with model 2 in 1 trace, we will be able to spot that and compute that. So precision of L1 and M2 will be less than precision of L1 and M1. So otherwise, also, if you don't impose that strictness, right? So you can take measure, a dummy measure, which for any log and model input gives you a value, constant value of 1, let's say, and that measure will automatically satisfy all these properties, all these 5 axioms automatically, but that will be a useless measure. So actually, I just want to stress again, I believe that this strictness on A2 and A5 is an important property, an important constraint to impose for the measure of precision. All right. So if I go back to the running example, so to say, and I now try to compare, well, these two cells, 0.874, so precision between M1 and L1, and the precision in this cell between M2 and L1, well, you will notice that this relationship between L1, M1, and M2 is exactly as in axiom A2. So log 1 is contained in model M1, and model M1 is contained fully in the model M2. So that's exactly the setting of the axiom A2. And then what axiom 2 tells us, that this precision value over here, 0.754 between M2 and L1 should be lower than the precision between M1 and L1. Right? So M2 describes these additional traces which make it less precise with respect to log 1 that you see on this slide. So this is now the explanation why these values are like this. At least if I start comparing them, of course, we can only compare them. So absolute value doesn't tell us much. And actually, this I think should be future work to figure out how to align or maybe stretch or compress those values that they match to the intuition of analysts. But if we just compare values, we can do a conclusion. This model is more precise or more fitting, etc. So we did also some evaluation with existing measures, synthetic evaluation, to see how they satisfy the properties, these 5 properties. So a bit more involved evaluation where we looked at more precision measures. So we said, let's take a synthetic log, and this notation means that I'm taking step A, 0, 1 or 2 times, and then I concatenate it with B. So basically, A, 0, 2 concatenation B is this event log. So we are taking this log, and then we're generating synthetic models that describe the log, and then describe the log and then trace AAAB additionally. So if I set x to 3, this will be one additional trace of AAAB, so 3 times occurrence of A followed by B. If I set parameter x to 4, it will be, well, my previous log plus a trace 4 occurrences of A concatenated with B, etc. So I add more and more traces to the models. And then also M star is infinite language. So A star, so any number of occurrences of A concatenated with B. And if you look at this plot, so of course, the precision of such a log, single log, should be dropping as the model grows in size, as the model allows more behavior, and then also should drop when the model supports infinite behavior. So if you look at the precision, eigenvalue precision, or our entropy-based precision, this is a blue line. You don't see it well here, but the values actually drop by a small amount. But there are also some clear measures that don't behave as expected. So right, this is just a straight line of ones. This is counterintuitively grows as the model becomes more and more complex, and then drops when the model becomes infinite. Here there is a correct drop that goes to the bottom, but then when we move from this complex model of 21 traces to an infinite model, precision goes up. So that's also not what you would expect normally. Another synthetic example, we took a log of 5 traces. Each of them is a permutation of 5 characters, A, B, C, D, E, right? So A, B, C, D, E, A, B, C, D, etc. And then we said, okay, our model adds more and more permutations. So M6 is a 6 permutation, M10 is a 10 permutation, etc. There are 120 permutations in total on 5 symbols. And then also we have a parallel model. So same, is model that can support same 120 traces, but we model it as a parallel 5 branches that execute A, B, C, D, E, and can produce any of the sequences. So basically, these are 2 language equivalent models, but have 2 different representations. This one, 120 and parallel. And this is the entropy measure, which it drops as expected, right? Smoothly, monotonically drops as the model becomes more complex. The measure between parallel and the 120 is the same, but if you look at other measures, you see some strange behavior going up and down, or going down, and then there is a sequence of same values going down, staying same value, and then going up. So if you look closely, you will see that none of these measures actually behaves as it would be expected according to the properties that I was presenting to you. So this is kind of also our validation that existing measures were not able to satisfy the properties that were proposed. So we did some evaluation for performance. It can run slow, but in most cases it performs quite well on our implementations that you can also get access to. That this is Entropy tool. It actually implements all the techniques I am talking today. Only for 2 logs that we experimented, computational precision and recall went over 10 minutes. Often much faster, but it can get slow, right? So here you see that it's 2.5 hours or so, but you get both precision and recall for that time. So it can get slow, but on the other hand, you get measures of very good quality, and if you just use them to calibrate, for example, your discovery techniques, that's worth doing. You will not be doing such computation live, right? It's more for offline calibration of the discovery techniques so that they perform better. All right. So researchers in conformance checking didn't stop with 5 properties. They say we need more properties. So they went for 21 conformance propositions. So this was proposed by Wil van der Waals in one of his papers. So he proposed 21 properties of conformance measures, this time for precision, also for recall, and also for generalization. So some of them, those that refer to precision and recall, well, are summarized in these tables. I will not go in detail what are those properties are. In summary, well, in some of them are just those 5 properties that I already showed to you, and others are generalizations of those properties. So that's kind of desired properties, how precision and recall should behave if we put the languages of model and log into correspondence and try to compare them. And you see that this measure on the right, recall G and precision R, they satisfy all the properties. And you probably know what I'll be showing next. This entropy-based precision and recall, these are the measures that satisfied all the properties also proposed in that extended repertoire of properties for precision and recall. So we were quite happy to see that this was done independently from us and confirming that these measures, well, have some quality in them. All right. So this was problem number 1 of doing conformance checking for exact matching traces, but also allowing models to describe infinite number of traces. So let's take a look at the second problem, which is partially matching traces. Right? So I already showed to you these 2 automata. Well, I showed you this process model 4. Describes 2 traces, and the log of 1 trace, A, B, B, C, E, now also shown as automaton. And of course, if I look at Venn diagram of those languages that this model and log describe, there is nothing in common there. So now the main idea comes. The main idea is very simple. If we will start injecting tau transitions into our automata, well, we'll start what we call diluting the languages, allowing also subsequences of original traces to occur in model and log. And from there, we will be getting a chance to see some shared behavior, some common subsequences that are present in the model and log. So for example, if I insert a tau transition here on step D in the model and on this step B in the log, well, now model and log both describe trace A, B, C, E, which will be in the intersection of that diluted version of the log and diluted version of the model. So that's kind of the intuition, but now you can ask, so, but how would you guess where to insert those tau transitions? And we said, okay, we will not bother of guessing, we will just insert them everywhere. So we insert those tau transitions for all steps in the model and log, and then we see all the common traces and subtraces, subsequences in the intersection of diluted model and log. Right? And the longer the common subsequences are, the more shared information will be in the intersection. That's also a very nice feature, right? So if I have a longer trace also, which is in the intersection, that also all its subsequences will be in the intersection. So that's what we do, and then you may guess what happens next. Next, we are just saying, okay, we need to short circuit model and log, diluted versions of them, and then we plug them in our original measures of precision and recall to compute these diluted measures of precision and recall. So if I go back to the example, so these two columns, column 3 and column 4, they show original precision and recall measures, right? If I just apply the technique for exactly matching traces. So if I now go to these diluted versions of model and log, right, and compute precision and recall, you see that these zero values are no longer zeros, right? So for example, M1 and L3, I was already showing you this example. M1 has nothing in common with L3. If I am doing my analysis based on exact match of traces, but if I dilute the traces, I'm getting some shared information, right? So if I skip D here, I have trace BA, and my log 1 also contains a trace BA. So that's the reason why we see non-zero values, because now model and log start to have certain shared information about those subsequences that they contain. So, but you say, okay, these are again magic numbers, and you're correct. And we proposed a range of other properties in our paper that was published in ICPM 2019, paper together with Anna Kalenkova. And those further properties allowed us to discuss the relationship between the measures. I will not go now deep into that. So, right, so there are some explanations of why certain value is less than another value, etc. So that's where those properties are applied. If you are interested, I guess take a look at the paper. I'll not spend time here. So also we looked at some evaluation that other people were doing, and so this log and 3 models I was showing to you. Process model 1 you may recognize, process model 2 you may recognize with this G and H interleaved over here, and process model 3 that I was showing to you, they were taken from the paper by Bodewijn van Dongen, where they were also proposing precision measures and use this simple data set to experiment and see how their measures behave. So this is the event log from their paper, and they had more models, right? I just took 3 models from their paper. And what they were doing in their paper, they were just ranking the models according to the precision with that one single log that you saw on the previous slide. And these are the rankings. So 1 is the absolutely worst model according to the precision. 9 is the best model according to the precision. So the higher numbers, the better numbers. This is our ranking of entropy-based exact matching and entropy-based with the skip. So this diluted version of exact matching precision. And these are our rankings. So if you take a measure which satisfies all those properties that we were talking about, all those 5 axioms and those extended list of properties, this is the ranking you should observe. This is the ranking you should observe. Bad news are none of the other measures produce such a ranking, and also none of the other measures are consistent. So all those rankings are very different. So there's no agreement also on all the measures, so to say. If you wish, I'm not trying to say that our measure is somehow better in that respect. We also don't agree with other measures, but we satisfy the property. So if there is consensus that these properties are valuable, then yes, we deliver up to them. So also, if I look at those two examples, process model 2 and process model 3, which one is better? Well, process model 3 is decided to be better in precision over model 2, right? So here we rank it as, well, model 2 is ranked as 4th and model 3 is ranked as 5th in the whole list of rankings. And these are exact measures of precision and recall, right? But if you think why that's happening, well, this model just allows more behavior because of this interleaving of G and H that are possible, right? So that's what we allow here. And if you think of it, if you, let's say, fix a number, let's say 5, and try or 10, and say how many traces of length 10 process model 2 has, and how many traces of length 10 model 3 has, well, model 3 will have less of those traces, right? If you just want to check it with pen and paper, do that exercise, and you will convince yourself that process model 2 actually describes a more branching behavior than process model 3. Well, also interesting to see that, well, here flower model for exact matching was ranked as 3rd. All parallel and round robin were ranked as absolutely worst. Well, these two models actually don't support any traces from the log. That's why they're absolutely worst. But when we dilute, let's say, round robin model, it becomes same as flower, and therefore the ranking flipped a bit. And flower and round robin are now absolutely worst, and all parallel model now can replace some traces from the log, and actually can replace all traces from the log, but also many additional traces, and therefore its ranking is quite low. Okay, so this is just a summary. We did experiments with this partial matching. These are very old results. We have more new results, and it runs now much faster. But still, I would say that my conclusion is that this partial matching precision is a theoretical concept, that you can compute it on toy examples, small examples. If you move to real world, it can take hours to compute those automata after dilution, simplifying, computing eigenvalues. That just runs for too long time. Though there is a paper, the journal extension of our conference paper, where we did many improvements on the time performance of this diluted version of precision and recall. So these are all the papers on conformance checking that I talked about. Well, actually even more than I talked about. So exact matching is paper number 1. Partial matching is paper number 2. Paper number 3 is the journal extension of paper number 2, where there are many more results to improve performance. The paper which is interesting and I didn't talk about is paper number 4. Well, it allows to do controlled partial matching. So it proposes a technique to control the number of skips you want to do in a model or log. And that is practically interesting, and then the computation is very fast. So it's comparable with the computation of exact matching, right? So it's just, you can say, I allow up to 3 skips in a model and up to 2 skips in a log, right? And you will be able to see certain similarities. So that paper describes how to do that. And paper number 5 is a tool paper, which links to the implementation. And from there, you can get command line tool where you give a model and log and compute all the precision and recall values. All right. So this was classical conformance checking. I was talking for 15 minutes. I was hoping I will go faster, so I will use maybe another 15 minutes to talk about the work on stochastic conformance checking, if you allow me to. So this is our more recent work. And if you look at this slide again, you may notice something that I kind of was hiding from you. I was not completely honest with you when I was talking about precision recall and conformance checking. So you can say, Artem, but where do these frequencies go? Are they at all taken into account? Right. So when we do the set, differences, intersection, etc., and you'll be totally right. They are not taken into account at all. They just ignore it. That's what classical conformance checking was doing to some degree. It's actually very hard to take this into account because models don't contain any information, any stochastic information about the frequencies. Let's say if I do A in this model, then B and C can happen with the same likelihood. Though in the trace, I see that after A, B will follow much more often than C, right? C happens in 4 traces, but they are rare traces. So B will be the most likely second step. But if models don't contain information about the probabilities, I mean, I don't know how to measure that quality of correspondence between what I see in the log and what I see in the process model. Actually, if I go to these lasagna models that the industry produces, well, these models contain some stochastic information. Well, they have here numbers on edges and numbers on activities. Well, at least where you start, and here there are some numbers. It's just very small font. I'm not sure you can see that. So these are the frequencies of observing certain steps or transitions. But if you also talk to industry, it will vary. You'll be lost in what they mean under those frequencies, because you will hear very different opinions about how they interpret these frequencies. It's either the numbers cannot match, or what that means if I enter a node with 100, number 100, and leave it with 80. What does it mean exactly? It's a bit subject of interpretations. So, but it would be interesting to do that, right? To do conformance checking where you account for perspective of the log and stochastic perspective in the model, like in this model where you have annotations about frequencies. There are not many works on stochastic conformance checking. On this slide, we see our works and some other works. Sandra Lehmann is also very active in this area. And these are probably all the works that were published to date, right? So if on classical conformance checking, there are hundreds and hundreds of papers, stochastic conformance checking is just a topic of the recent year or maybe 1.5 years. And I will want to quickly show you the work on entropic relevance that we published in ICPM 2020. And I want to thank my collaborators, Alistair Moffat and Luciano Garcia Banuelos, who are co-authors of this paper. Now we also have a PhD student, Hanan Al-Kamash, who is helping us to push these ideas further. So expect some more works from us in this area. But let's finally get to the idea of this measure. So the idea is to do conformance checking via compression. So like in compression, like you think of zip or R algorithm for compressing, for archiving your files. So that's something similar we do with traces of the event log. We compress them, and we compress them using models, candidate models that candidate models to explain the event logs that is given. So imagine we have a true process, and then event log is a sample of that true process that we don't know. And then we have 2 candidate models, process model A and process model B. So we can compress. So what we do, we kind of compress a log using process model A, and basically we obtain some representation of log in bits. And then we also compress more event log, but now using model B, and also get some representation in bits, compressed representation in bits, like your zip archive file, something like that. And then the compression, which is smaller, it means that we got that compression using a better model, a model that describes event log better. So because if you think about it, a better model will be that model which contains more frequent patterns from my data. Right? If my model contains many frequent patterns from my data, I can use those patterns from the model to compress, to find an alternative representation of that data to compress it. And that's an idea, and that's kind of I already explained to you the intuition why that works in general. So just an example to illustrate how this all works together. So I'll quickly introduce the notion of minimal description lengths for compressing information. So taken from the book on information theory. So imagine you have 8 horses that participate in a horse race, and this has the likelihoods of winning for each of the horses. So horse number 1 is a champion, wins in half of the races, and others, well, these are corresponding probabilities. So then you may pose a question. So if I'm sending a message about horse to my friend, how long that message on average should be? Right, so what is the minimum description length of such a message? One way to get the description of a message is to say I have 8 horses from 0 to 7. Well, I can use 3 bits to encode them, all right, and then send 3 bits to my friend. And I'll be using 3 bits on average. But you can do better because you can be sending shorter messages for frequent winners and longer messages for rare winners. And basically, your minimum description length for such a message is equal to the entropy, Shannon's entropy variable, which is this event of horse winning a race. And if I compute the entropy of that random variable, well, the value is 2 bits. So I need to send on average 2 bits instead of 3 bits, which is shorter. So it's a better description of the random variable. And this has a sample messages that I can be using. So if horse 0 wins, I can send message 0. If horse 7 wins, I can send message 1, 1, 1, 1, 1, 1, which is 6 bits. But because I'll be sending this rarely, on average, I'll be sending 2 bits. Trace compression. So now we come to the compression. Now we come back to the domain of process mining, to traces and models and logs, etc. So what do? We take event log, we take each trace of the event log, and then for that trace we decide, can we replay the trace in the model? If we can, yes, we will encode that trace using the probability of that trace in the model. And our model is stochastic model. It contains information about the likelihood of traces. And if it cannot be replayed, then we need to find some alternative encoding of that trace. We need to come up with another scheme, and we call that universal model or background model. Basically, then we find a way to encode that trace, which is more costly, but still, we will get to the point where we can encode that trace. And in addition, we need to encode the decision. If we want to decode, right, if you want to unzip our log, eventually we need to understand where the coding came from the process model or from the background model. So we need to store also decision about which encoding was used. So, and that is also the cost that is included in our measure. So it works like this. Like if we think about how this measure then should behave, the compression of the log, it behaves the following way. So if my model is small, if I just make a model of one node or one edge, it will probably describe very little traces from the log. If my model is small, it's not fitting many traces. But then many traces will be encoded using the background model. So costly encoding, this is a blue line. Very little traces will be encoded using the process model, and this is the green line. But as the model gets larger, more and more traces fit the model. That's kind of normal thing you would expect. So model becomes larger. So the number of traces that get encoded using the model increases, and that's why the green line rises slowly. At the same time, we encode less traces using the background model, and the blue line decreases. The yellow line is a selector line. So to encode the decision, are we encoding a trace using a model or log? And this is usually a very small cost, at most 1 bit if we are in full uncertainty, 50-50. Either we encode using model or log. Usually it's better. And then our total compressed size is a sum of model coding cost, background coding cost, and the selector cost, coding cost. So I'll skip this explanation. These are just explaining how different components of our total compressed size are behaving on different areas of this plot. I also explained it to you in words. Also, what is important here, of course, is the purple line. If you want to be completely lossless, we not only need to store the encoding of the log, but additionally, we need to store the encoding of the model to be able to later to decode it. But we keep that cost separate as a cost of model complexity. I'll show you in a second why we do that, is to be able to kind of contrast the complexity of the model and the compression it produces. So this entropic relevance is basically obtained as a sum of these three costs. And then this is a formula of how we compute entropic relevance. So entropic relevance of event log E to model A is measured in bits per trace. So it's basically a number of bits we need to use to encode a trace on average in our log. This is our probability of that a trace from event log E fits our model. So let's say 80% of traces fit our model. So probability will be 0.8. And this is then the selected code to encode a binary variable, random variable with probability 0.8 and 0.2 to make that decision, plus the average cost of encoding one trace T from our event log under the knowledge of our event log E and automata our model A. And there can be two cases. Sorry, I now again run in front. There can be two cases where a trace fits the model, and then we can use the probability of the trace in the model to encode it, just as we did it with encoding probabilities of horses winning the race, right? We just take a logarithm of that probability, and that's the number of bits we need to encode our message about horse winning a race, or here trace being present in the model. And if it's not fitting the model, sorry, my animation again is playing tricks on me. If it's not fitting the model, then we use a background model. And in this case, we are doing very simple encoding. We encode each event of the trace separately with the number of bits we need to encode that event, right? So if let's say the alphabet is 256 possible events, we need 8 bits to encode that. We do +1, right? So we take logarithm of 256. We take +1 because we also encode end of trace symbol, because if we were to decode it, we need to encounter that end of trace symbol and be able to decode, well, say, this is the end of my trace. Now I'll start decoding the next trace that is in my encoding. And because we have now, that many events in the trace, +1, well, there is a multiplication. So we take the length of the trace, we add the end of trace symbol, and then each of those symbols, events, is encoded using that many bits. And that's basically the end encoding. How it works in practice, let's say this is our DFG. We encode it as a SDFA, so a stochastic deterministic finite automaton. So there are some probabilities on edges of taking certain steps. And then once we get an event log, well, we do the compression, and then we obtain the average number of bits we need to encode a trace. And in this case, if we use automata A1, obtained from this DFG, we need 4.22 bits. And if we use automaton A2, we need 5.49 bits. So the model with smaller bits compresses our log better, so it's a winner, right? So now A1 is a better representation, description of my event logs than the model A2. So that's how we can do these decisions, and these decisions now incorporate the stochastic information from the models, because the encoding was done using probabilities from the models. So these are some component costs that you see from model cost, background cost, selector cost. You see here that the model cost is higher. More traces fit the model, and therefore we encode using the model more often. It's more cost from the model than here, 255. but background cost is very low because, well, we use it rarely. Many traces fit the model. Selected cost is also very low here. So we just need to, on average, we need to use 0.29 bits to tell which model was used, process model or the background model, to encode the trace. These are some machinery, so just explaining in more detail how the coding does for each of the traces. Let's say I take a trace AB from the log, it fits my model. So I'll be using model encoding costs. That's how many bits I need to use to encode a trace with a probability, which has a probability of 0.25. Sorry. It has this probability of the model, but because it only happens in a quarter of cases, its contribution to relevance is only 0.6, the quarter of that cost. So these are the components of the relevance that come from model encoding. Only one trace doesn't fit the model. This is the component of relevance which comes from the background model. This is the selector cost, and the relevance value is the sum of my model encoding, background encoding, and the selector cost. Just explaining in a bit more details how we obtain the total cost of encoding a trace. Evaluation, we did some evaluations with real life logs just to observe if the measures behave how we expect they do, right? So this was anticipation that I showed to you on previous slides, confirmed here with, let's say, sepsis log, right? So background cost decreases, model encoding cost increases, selected cost is really minimal, but we need to include it because of the, well, if you want to be fair and be able to decode the log, we should include it. And this is our cost of the, well, entropic relevance cost. How can we use it? Well, we can compare different models as how well they encode event log. So here we use 3 discovery techniques. One from Sander-Lehmann's, directly flows minor, those are orange dots, and 2 approaches from Celonis. Actually, the engineers from Celonis send us some models, 10 models discovered using Celonis PE technique, and then ones discovered using Celonis VE technique. I don't remember exactly now what those abbreviations stand for, but that is not that important at this stage. And basically, better models are closer to the 0 point, to the 0 point. So they should be compressed. They should be they should allow us to compress event log better, right? So they should be lower and closer to 0. So you see that often that technique by Sander-Lehmann's is superior to industry models. But also, if you look at the area of primary interest for business analysts, so those smaller models, because you will not be showing models to analysts of size 100, 150 nodes and edges, so probably maximally up to 50. So the competition is a bit more involved here, right? So this model from Celonis is also of interest here as well. Like if I zoom in, you'll probably see that blue dots and purple dots are competing quite well and maybe even produce better models. And here as well, you see that blue models are quite good. So this was conclusion, but that's how you can use this technique to decide which models represent the stochastic information from the event log better. And that's of course important because if you want to know what happens in the real world, you also want to know what happens frequently in the real world, right? So you want to know that information about frequencies in the real that come from the real world. Okay, that's my last slide. It took a bit longer. So my conclusion. So look no further. Sorry, for measures which come up with a value 0 to 1. Or entropic relevance is actually not on the range of from 0 to 1. It doesn't have upper bound, but well, it's intended, right? It's kind of intended and designed to be that way. So for measures, well, please look further. It's a joke, rather a joke, but our measures are also quite good, I would say, to be used for process mining and assessing the quality of models discovered from event logs. They satisfy many properties. Exact matching precision runs quite fast, The extension with the controlled number of skips in the XOC paper that I only listed on the slide also performs quite fast. So you can also do partial matching, recall and precision. Entropic relevance, the measure with stochastic properties that I showed you, runs extremely fast. It's a linear time on the size of the information in the event log. So for example, we took BPI Challenge 2018, which has 43,000 of traces and close to 1 million of events. And when we were measuring entropic relevance with models between 25 and 238 nodes and edges, well, on our small computer, it ran always faster than half a second with very naive implementation. It's super fast. All the techniques I showed to you, I implemented in the Entropia tool. So please download it, use it. If you have problems, ask us, we will support you. Already many researchers asked us and we indeed supported them. Even recently, there were several requests. And for future work, so what I think is interesting next steps, some kind of, I made it sound like everything is solved. Of course, not everything is solved. Many problems are still open. For the non-stochastic version of precision and recall, well, we still cannot handle unbounded state systems. So automata that we generate need to be bounded for finite. There are some ideas how to approximate, but no time, so to say, to write those papers. So that's one issue. Another issue that can be addressed is empirical study that will allow to establish usefulness and intuitiveness of the conformance measures, right? So 0.8 is better than 0.7, right? So if I compare, I can do this conclusion. But is value of 0.8, well, intuitively conveying correct message that that is a good model or not? Maybe saying 0.8 sounds like a good model, but it's really not a good model, right? So it's kind of adjusting those values, and I think only users can suggest us how to scale those values. So right, all those measures I showed to you are monotonic, right? I add more behavior, the value of a measure drops or goes up with every trace, but how fast it should go up and down, that's what we don't know. For entropic relevance, we experiment with other background models, so we try to compress better. There are some technical reasons why to do that. If we can compress better, kind of we are less biased in our conclusions, because well, conclusions of which model is better depend on the background model we are using. So currently we're using a very naive model. Every event is encoded as if it's equally probable in the event log, and that's not true. We can use information from event log or automaton to compress those unfitting traces even better. And also, of course, now as we propose this entropic relevance measure, we would like to explore the algorithms to discover models that will optimize for that entropic relevance. So see what comes out of it. So that's also one of the steps we want to do in future work. Okay, I said too much. I think I will stop here. Thank you for your attention. I hope you enjoyed this talk. So I'm open for questions. So please, if there are any questions, ask.
Thanks a lot. Thanks a lot, Artem. That's actually really a lot of food for thought now. So I think we can check whether someone asked in the chat. No, there's no one. Maybe someone would like to unmute and just ask the question out loud.
I have a question actually. Even may I ask?
Yes, sure. Please go ahead.
Okay. Actually, I have two of them, and the first one is, I think, more or less technical. In the first part of your talk, I think it is 18th slide. you showed a table with measurements, and yeah, this one exactly. And you stressed that in some cases the computation is is longer than in other cases. And my question is it only about the size of models, etc., or there are some specific problems for these how to say outlier cases?
That's a very good question. Actually, there is no, well, it's very hard to identify those cases and what leads to those long-running example, well, inputs. Right, so at the end, we're computing eigenvalues of a matrix, and it's also known from linear algebra, etc., and algorithms of computing eigenvalues, that it can be the case that we can compute an eigenvalue of a big matrix really fast, and then an eigenvalue for computing eigenvalues of a small matrix can take a really long time, right? So there are some iterative methods, and some feature of a matrix can guide the computation in a very long iterative procedure. And there is actually very, also in the research on computation of eigenvalues, insights on which cases lead to complex situations and which cases lead to simple cases, right? So I didn't look further than that, right? So we just use it as a service. There are people who compute eigenvalues. We take their techniques. We know that it's polynomial in the worst case. You can have polynomial techniques to compute it, but still, if you have big matrices, it can take quite a while. So maybe there can be a work that takes into account the specifics of the data sets we are working with. Maybe if you work with event logs and the type of data, there can be some conclusions, but I would say this is out of scope for my research. Maybe somebody else can do that.
Okay,
yeah.
Okay, thank you.
But just to add quickly, it's very hard to draw conclusions based on the input, how long the technique will run. Sometimes, in most cases, it runs okay, but sometimes it gets into those intricate, well, complicated situations, and the computation progresses for a long time.
Okay, thank you. That's interesting. Yeah, I think it is a good direction for how to say computer science theory specialists to look into. My second question is is more general and is about different conformance checking measurements. Usually, 4 of them are considered. So fitness, precision, generalization, and simplicity or complexity. And can you add something about what your entropy-based approach, of how your entropy-based approach can be applied, maybe, I don't know, for generalization measurement?
Specific. So thank you for the question. Sorry, I hear some background noise when I'm speaking. Yeah, so actually, I will disappoint you a bit. I cannot really, so you're totally right. So usually we consider 4 quality dimensions, precision, recall that I talked about, but also the model should be simple, right? So we don't want a very fitting, precise model, which is spaghetti. So we want a simple model, which is precise and fitting. And we want that also that model generalizes for the behavior, right? So log is just a sample of the observed behavior, but right. So when we discover a model, we want that it represents a log well, but also by magic guesses correctly the traces that the log was sampled from. So does inferences about the original system that generated the log. So there are only very few techniques on generalization, maybe 2 or 3. I had a look at them. I only know that the properties that Will van der Waals proposed in that 21 conformance propositions paper, many of those, well, many properties are not satisfied by those techniques. So there is clearly a perfect chance to do research on generalization measures, how to directly apply these concepts of entropy to do generalization measurement. I don't have idea at the moment, but if I was be thinking how to do that, I would be looking into some methods in statistics to measure generalization, right? Because what we are, because I think statistical methods, they can learn something what is not observed yet. I need to explore further, but that's my feeling. And maybe maybe those methods can be combined with entropy, but I don't have a better answer at this stage. But a very good question.
Okay, thank you. Thank you. Then I have no more questions.
Other questions? Okay, well, someone is listening, is thinking on asking something else. So I would ask you probably a generic question, because, well, since me myself at least, I work on this extended, let's say, PetroNet model. So it would be extremely interesting to hear at least a comment on how do you think these measures would extend to more expressive cases of PetroNet. So let's not go very far, but say picking up PNIDs that you worked with, or models that Massimiliano De Leone was working on, this data PetroNets and such. So what do you think about those ones? Maybe you had already some thoughts how to extend.
Very good question as well. Yeah, so we work with Jan Martijn on also the approach for modeling, process, and data together. So I think Jan Martijn talked about ISM approach, information systems modeling, last week. And basically in that formalism, so the semantic of that formalism is again a reachability graph. Right? So it's a pattern with identifiers, which can potentially describe, well, potentially can describe unbounded behavior, but if it's bounded, and then, well, I think I listened to the questions of that session. There was a question about database, and the database we assume has always a finite amount of statements in it, of records. So then the underlying semantic of that formula is a reachability graph again. So it's a state machine that generates behavior and transformations. So then you can measure the topological entropy of such product, synchronous, well, product of data automaton and process automaton. That can be a first idea. Not that I thought about it further, but that can be a first idea. Maybe it's possible, and now again I'm just thinking out loud, to use some ideas from the area of of correlations for categorical data, right? So in those works, what they do is they measure correlation between, let's say, a numeric value and a category, and so some set of values, by looking at the entropy. So let's say if country Australia corresponds to many on some numeric values, it's a high entropy of that relation. So maybe it's possible to correlate, well, think of activities in the model as categorical things. Activity A, activity B happens, and the manipulation of data that activity is doing as some numeric value, if the data is numeric. Right, so activity A worked with value 5, 10, 100, and therefore its entropy is higher than activity B working on a value 10 only. So it's again just thinking out loud. So maybe something is possible in that direction.
And would that, well, probably extending this thinking out loud, maybe would it affect also the performance of the measure computation dramatically, or you don't really think so? Because, so for example, if you, I actually agree with you on this suggestion regarding the automata-based approach, where you would probably just consider an automata that represents the all possible data evolutions, like in the case of PNADs and data models that they manipulate. But do you think that, so if you need to consider all these possible evolutions, probably it will be rather, well, I don't know whether it will be actually rather big, but still, would it affect the performance of your approach? Because you were also saying that it's actually relatively fast to compute various.
I think that will impact performance because the automata will be huge in size, right? I mean, because the number of possibilities of how to match process behavior with the data will just explode, and then the matrix will be huge, right? I mean, I think in practice we were computing.
Yeah.
I think we were computing in practice some matrices, eigenvalues for matrices like 10 million by 10 million, right, in sparse representations. But there is always some limit to that, right? I mean, 10 million is not that much. For 100 million is also not that much if you think of a realistic system.
Yeah,
so
right.
Once you
yeah, sorry. I just wanted to say that actually is also very interesting. How would one try to solve those problems for realistic systems when you really have those huge matrices? As for those, you need really a lot of computational power. So probably running it on I don't know, some kind of bigger server. I think it's probably also an engineering question that one might have.
So right, so maybe right, so it's, maybe you can start playing backwards. Maybe you don't need such a precise measure, right? So we wanted to get a precise precision, right? So now you can say, okay, I give up the computations to actually be imprecise, and there are some ideas, there are some results on how to approximate eigenvalue of a matrix, in which let's say instead of computing exact value, you can say in which interval it lies, and then your computation becomes imprecise all the way up to the precision recall value. So it's a balance. So if you want to have such a measure which is sensitive to a single trace, as I was saying, right? So one trace will detect the difference. You will need to spend some of the computation there. Right? But also, if you compare it, actually nobody did it as well. It would be now interesting to compare existing measures by performance. Right, so my feeling is that many of them will not perform better than these times you see on this slide, and give such good results. Right, so that's but that's a feeling only. When we're doing experimentation, nobody has written a paper on that. So performance comparison is another dimension. If you want to be precise, you need to spend some effort. Maybe you can give up some precision. Yeah.
All right, thanks a lot. for that. I think there was someone who wanted to ask a question. I saw raising hands, so please unmute yourself and.
Yeah. Hi, Artem. Just have a quick question. For this entropy conformance checking method, so I saw it's a kind of to check how this model match to a event log, right? So the event log have many different traces. So if I just want to check one trace, one single trace, that may not happen. It's from an unknown model, or maybe. So when you only want to check, is this one trace match this model? Is this method is good for this this experiment, or it's just give us a yes or no answer? Is there any useful information for this experiment? Just have one trace.
Yeah, one trace is, yeah, it's a yes or no answer kind of, and you can get it just by trying to replay that trace in the model. So, right? It's
okay. So is there any other information like the numbers maybe meaningful for us to? So when you match this trace to the model, you do the alignment or do some other techniques?
Yeah, so you can do alignment, right? And then you can get a binary answer, or you can see deviated steps in the alignment. What you can get maybe additional to that, you can, if you do partial matching of the trace doesn't fit, well, you can quantify it, the discrepancies by doing the dilution of that trace and see how many matching steps you will discover, right? But it's some value. Actually, the good point you raised, I can maybe advertise a bit the words that I didn't talk about because it was only listed on the slide. So these are the papers on classical conformance, and on stochastic conformance. We just recently got a paper accepted with Sander Lemmans and Willem de Rast and Tobias Broekhoff. Basically, this paper does something similar to alignments, where you have synchronous steps, but also does well, it in a stochastic kind of fashion. So it contains information. What is the likelihood that a certain step will be synchronous or asynchronous? So that can give you a more informative answer than just a number, right?
Okay.
So for a single trace, you can just get an answer yes or no, fitting, non-fitting. You can get from alignment, you can get information about where the deviations happen. You can run our partial matching conformance to also get some feeling of how well that trace partially matches to the model. But that also somehow is a reflection of what you see in the alignment, right? The more asynchronous steps you will have in the alignment, the lower will be our partial matching values.
Okay. Okay. Thank you.
Thank you for the question.
Okay, we have one more. So please go ahead.
Hi. I was thinking more about where this the metric can be applied, and I like the aspect of the monotonicity. And well, it's a pretty old topic, but this the trace clustering. So there was a method from 2012 where you try to cluster traces in a log, and this is done by building a small cluster and looking at how well what is the accuracy of the model discovered of those traces based on the conformance between the traces and the model. So I guess this approach can be used because of the monotonicity property. Is it right?
Yes. Yeah, that's right. It can be used in that case to assess the quality of the model discovered from a cluster, right? In a well, it's the question is always, can you be used in the genetic mining algorithms, right, to assess the candidates? But again, the trade-off, is it fast enough for the genetic mining approach to try the candidate models and assess their quality? Will that lead to less iterations and speed up? And these are valid questions, all the valid questions, that's true. So, but technically that can be applied in any context where we currently apply conformance measures, precision and recall, in any context.
Thanks.
Okay, so do we have someone else? All right, it does not seem so. Okay, so, well, let's call it the day then. So for you, for sure, for us, it's just the beginning of the day. One more time, Artem, thanks a lot for this extremely interesting presentation. And there are really lots of things to think about and many ideas to pick up for other researchers who especially work in the area of process mining. So a round of virtual applause, unfortunately, but thanks a lot. And I hope to see others during the next sessions of this event. So see you soon. Bye.
Thank you, Andy. Thank you, Andy, and thank you for inviting. Thank you for everyone for attending.
Thanks, Artem. Thanks again. See you. Bye.
Bye-bye.
Bye-bye.
Thanks for interesting talk.